what is the point of this class, right? The point of this class is to get you familiar with the concepts of astronomy. Um, and what is astronomy? In general, astronomy is the study of everything beyond the Earth. Uh, and so that means that includes things like the moon and Mars and the planets in our solar system. But we're not going to spend a lot of time on that because we have another course in the department called AST 112, and AST 112 is introductory astronomy. Sorry, this is AST 112. The other class is AST 111. Pardon me. AST 111 is more about planets and the solar system. So, in other words, small stuff, and once you start talking about astronomy, things like entire planets are, small stuff. Um, Whereas this class is more about, as I said, stars and galaxies, right? The really big things really far out there in the cosmos. All right. One of the other things that we're going to talk about, one of the other recurring themes of the class is not just what do we know today, but what did we used to think, right? Because in order to understand why we know what we know today, we need to understand how we got here. We need to understand what did people think centuries or millennia ago, and then what did people discover that taught them that things are different. So 1,000 years ago, this is an old woodcut of essentially a map of the universe, right? 1,000 years ago, people thought that the Earth was sitting still at the center of the universe, and that the sun, the moon, the planets, and the stars all revolved around the Earth. With so with the starry sky just hovering above the Earth's surface out there, a few thousand miles up, circling the Earth. And that's neat, but that's not the most interesting thing. The most interesting thing is why. Why did they think that this was literally a map of the universe? What did they see? What did they observe with their own eyes, looking at the sun, the moon, the planets, that led them to this conclusion? That's the interesting thing, right? Yes, they were wrong. Okay, the Earth is not the center of the universe. The sun is not going around the Earth. Okay, yes. They were wrong, but they weren't dumb. People 1,000 years ago were not dumber than we are today, and they were no smarter than we are today. So they saw something. They gathered some evidence that led them to the conclusion that the Earth was sitting still and that the sun and the stars and everything was circling around the Earth. What was that? What did they see that led them to that conclusion? And then what did somebody else see later on that led people to conclude, oh, the sun's not going around the Earth is going around the sun? Somebody had to see something that nobody had ever observed before, that made us realize that the universe is not structured the way we thought. And that's a big lesson, right? Today we know that the sun is not going around that the Earth is not, other way around. Today we know that the sun is not going around the Earth, and in fact that the Earth is not the biggest thing in the universe. That in fact the sun is much, much bigger than the planets, and that our sun is not even the biggest star, right? Somebody had to realize at some point that the sun is a star. Even though to the naked eye, you would look at the sun and you would look at the stars at night and go, no, those are two totally different things. The sun looks very different than stars because it looks bigger and brighter. So somebody had to see something. Somebody had to make some observations. Somebody had to notice something in the universe that said, oh no, the sun is a star. And that the only reason why the sun looks different than the stars is because it's a lot closer to us than the other stars are. And then somebody had to notice, somebody had to draw the conclusion that actually the sun is not even the largest star. There are some stars, there are a bunch of stars that are smaller than the sun, but there's also a bunch of stars that are bigger than the sun. And that there are other objects in the universe that are so far away that they look tiny on the sky, but that once you start analyzing what you're seeing, you notice that they are much, much bigger than stars. This is a picture of the Great Orion Nebula. What is a nebula? Right? This is our first piece of vocabulary for the class. What is a nebula? Well, what does this look like? It's a cloud, right? It looks like a cloud of gas, and that's what a nebula is, right? A nebula is a term for a cloud of gas floating out there in the galaxy. And there are lots of different kinds of nebulas, but specifically, this is the Orion Nebula is the type of nebula where stars are being born. So all of these stars that you're looking at right here are newborn stars born out of this cloud of gas, out of this nebula. And in fact, if you notice, like, well, wait, this cloud of gas has actually several hundred stars inside of it. Well, that means that this nebula must be much, much bigger than any of these individual stars. So that Theta Orionis 1c is this much bigger than the sun, and Theta Orionis 1c is that one right there. So this whole nebula must be much, much bigger than even a star that's significantly bigger than our sun. Right. This is a different kind of nebula. This is what's called the Crab Nebula. Again, it's a cloud of gas, so it's a nebula. But this is a type of nebula called a supernova remnant. Because when some stars die, they blow up as these giant explosions called supernova, and then this star exploded about 1,000 years ago in the year 1054. We can actually say when this star exploded down to the day. We know it was July of 1054 because there were people around back then to write this down. You know, when a star explodes in the sky, it tends to get your attention. And so people wrote down, oh, what was that? And when you look at this exploded star 1,000 years later, it blew up and shot out all of this gas, and that gas has become this cloud, this nebula. So there are different types of the same object, right? Not all stars are the same. Some stars are big, some stars are small. Not all nebula are the same. Some nebula are starbirth nebula, right? Nebula where stars are being born. Some nebula are the kind of nebula you get when stars die. We'll see this a lot in the class, is that when you look around the universe, you find different types of objects, stars, nebula, galaxies, but that every one is a little bit different for slightly different reasons. And that makes things interesting. Why? Why are nebula different than each other? Why are stars different than each other? There's a story to be told there. There's some discoveries to be made about why they look the way they look. And that's part of the fun, is figuring out, doing the detective work to say, why is this star like this? Why is this nebula like that? That's all part of the fun. We're getting towards summertime here. If you go out, hard here in the city. It's hard. It's hard here in town. But if you get out into the desert, someplace where it's nice and dark, and you get away from the city light pollution, during the summertime, you can see stretching from horizon to horizon the Milky Way. The Milky Way is this big band of hazy light across the sky, because what you're looking at here is you're looking at our galaxy edge on, right? This is a different view of the whole sky unrolled like a map. We live in what's called the galaxy. The galaxy is a big disc-shaped collection of hundreds of billions of stars. And yet when you've got hundreds of billions of stars really far away, you can't pick out the individual stars anymore, or at least it's harder to pick out the individual stars. And so the collective light of all those stars so far away creates this hazy, milky colored band of light. That's what the Milky Way is. It's us looking at our galaxy edge on. And in fact, our galaxy is just one of billions of other galaxies. This is a totally separate galaxy called the Andromeda Galaxy, with hundreds of billions of its own stars. But it's so far away that we're not inside of it. We're able to look out at that galaxy and its billions and billions of stars from a distance. So this is what a galaxy is. A galaxy is a collection of hundreds of billions of stars all together in space. And there are lots of different stars. Just like there are lots of different types of stars and lots of different types of nebula, there's also lots of different types of galaxies. And each of them looks a little different because each of them has something slightly different going on. They all have a slightly different story to tell. And why does this galaxy look like this, but that galaxy looks like that? That's an interesting question. We'll get there. We'll get there. All right. And then when you zoom out and you look as deep as you possibly can into space, what you see is, well, this picture is what's called the Hubble Ultra Deep Field. This is one of the deepest pictures ever taken using the Hubble Space Telescope. That's why it's called the Hubble Ultra Deep Field. That's one star. That's another star. So these are two stars in our galaxy that are in the foreground. So those are in the foreground. Everything else in this picture, every smear, every swirl, every speck, every little light source in this image is a separate galaxy made of billions of its own stars, much, 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 much further in the background. And so as you look deeper into the universe is filled with galaxies, and then those galaxies are filled with stars, and those stars are orbited by planets and people and movie theaters. Who knows? I don't know. We don't know that much to that level of detail. But maybe. How do we understand any of this? How do we comprehend any of the stuff that I just said? Right? How do you know that anything I just said is true? How do you know I'm not making stuff up? Right? Science is not about taking my word for it. Right? Just because I said it, just because I'm on this side of the microphone doesn't mean I'm telling the truth. Right? We have reasons to think what we think we know about the universe. There are reasons for why we think stars work the way they do and galaxies work the way they do and nebula and all of them. Right? Part of this class is to say, why do we think that? Why do we think we know what we think we know? What's the evidence? What did somebody see? What do we understand about the universe that leads us to the conclusion of stars work like this and galaxies work like that? And the Big Bang works like this. Or worked like this, I suppose, past tense. We're going to focus a lot in this class on evidence and observation, right? Because, right, science is not just a list of facts that you memorize, right? Science is a tool for figuring out how things work, right? I think a classic example, to flip back to the previous slide, a classic example is gravity, right? People have known forever that what goes up must come down. But people worked for thousands of years trying to understand why. Why does what go up must come down? And then 300 years ago, Isaac Newton sort of figures out that, there's rules. There's a principle behind why what goes up must come down. And he called it gravity. Right? Before Isaac Newton, nobody called it gravity. It was just called, things fall down. What do you want? Right? And so Isaac Newton came up with a great idea to explain why things fall down, why what goes up must come down, how this gravity thing works. And it worked great, right? Newton's idea, Newton's theory of gravity worked great. But eventually, people realized that Newton's idea of gravity didn't work in all cases. There were little oddities where gravity didn't quite work the way Newton said it should. And nobody could figure out how to solve for these anomalies until Einstein. One of the things that made Einstein famous was that he came up with a new theory of gravity, which he called general relativity, for reasons I'll get into later. And it was basically a new theory of gravity, a new theory of gravity that said, yeah, it turns out that Newton is wrong. Actually, gravity works differently than that. Here's how gravity works. It works according to his theory of general relativity. But what makes it such that Einstein's theory is better than Newton's? And the answer is the evidence. Right? That if you just have an idea, that you're throwing out there, a guess, that's what's called a hypothesis. Right? A hypothesis is just like, I got an idea, I think something works like this. But then you go out and you collect the evidence, make the observations, point your telescope, look at the universe, see what you can see. If all of the evidence backs up your hypothesis, then your hypothesis graduates to becoming a theory. So what is a theory? Right? A theory is not just a guess. I know that in everyday English we sort of say like, well, I've got a theory, and what we mean is I have a guess, I have a hypothesis. A theory is not a hypothesis. A theory is not a guess. A theory is the best idea that we have today, based on the evidence that we have today. Right? In order for something to be a theory, by definition, if something is a theory, that means it's the best idea we have today based on the evidence we have today. And so Einstein throws out this math that says, actually, I think gravity works like this, but just because Einstein says it doesn't mean it's so, right? People had to go out and collect the evidence and say, wait, does gravity work the way Einstein says it does, not the way Newton says it does? And it turns out it does. So then they found the evidence that said, oh, Einstein's right. Einstein's idea does explain gravity better than Newton's idea does. And therefore, Einstein's idea graduated to becoming his theory of general relativity. Right? A scientific idea lives or dies by the evidence. Right? The only reason why we think we know what we know is because we have evidence that leads us to the conclusion that things work like this and not like that. And so a lot of this class is going to emphasize not just what we know, right? This is not a class on stamp collecting, right? This is not right? That if you say you understand something, or if you think the universe works one way, that claim requires evidence. And the more extraordinary the claim, the more extraordinary the evidence backing it up has to be. Right? I can tell you, the universe is 13.8 billion years old. And that's a bold claim, to know how old the universe is. So if I'm going to tell you something big like how old the whole universe is, I better have some pretty darn compelling evidence to back it up. And we do. What is that evidence? We'll get there. Right? But this class is not just about what we know today. More importantly, it's about how we know it. It's about how did we get here? It's what do we see? What do we observe? What evidence do we collect that leads us to this conclusion? And also the class is going to be partially about what we used to know, or what we used to think was going on. And then what did somebody observe? What evidence did somebody collect that made us change our minds? Why are we going to talk all about this? Because we haven't answered all the questions today. There are still a lot of questions that need to be answered. And how will we know when we have the right answer to the question? Because we'll have the evidence that tells us. Everything we know today could very well be tossed out the window in a year, 5 years, 10 years, if the evidence arises, right? Tomorrow, might be the day when we see some new evidence that no one's ever seen before that makes us reevaluate our ideas. Just like people had to do when you're like, oh, we've been thinking gravity worked the way Newton says it does for centuries. And then somebody saw something. Somebody saw those anomalies, those oddities that made people realize, oh, things don't work like the way Newton says. We need a new idea. We need a new explanation. And, then Einstein came along. There is every possibility. Part of the exciting thing, like I said, is that astronomy has history, but it is also modern. That people are making observations today. People are trying to answer the mysteries today. And that discoveries are going to be made while we're in this class together that might make us reshape our view of the universe and of our place in the universe. That there's always, tomorrow is always the possibility that we see something revolutionary that makes us reevaluate our place in the universe. And that's also part of the fun. This class is, if you don't mind me saying, I'm a little biased, but if you don't mind me saying, this class is a lot of fun because it's got a little bit of history to it. Right? We get to learn about how people did cutting edge science in the 1700s, 1600s. But also how we're doing it today. How are we making the big discoveries today that might mean that somebody sees something totally new and surprising tomorrow that means we're going to have to rethink our theories. Right? Science is fun and exciting because it's never done. Science is never complete. There's always the possibility that you see something new today that no one's ever seen. And so one of the reasons why we're going to focus so much on collecting evidence and drawing conclusions is because that's how science works, right? You don't just make stuff up. Our best theories are theories by definition because they have the overwhelming weight of evidence to back it up. And so if we're going to say we know something about a star, a nebula, a galaxy, the universe in general, it's because we saw something, we made some measurement, we have some evidence that leads us to that conclusion. So how do you do that? How do you do that as a member of this class? As an astronomer in training? I mean, I know you're not, most of you are probably not astronomy majors, but you're astronomers for this semester at least. Congratulations. You're astronomers now. So that's going to be part of this class, is to say, how do we do this? Right? That's all part of the fun.